Our webinar today is on safety critical clearance and creepage checks and how HyperLynx DRC can help make this important part of a design review much faster and more complete. Even though HyperLynx DRC is in the family of HyperLynx simulation tools, it is not a simulator, but instead does a comprehensive geometric analysis of the PCB. It can perform a rules-based verification of your design, ensuring consistency and greatly reducing the time required for design review. There are 3 levels of licensing available for HyperLynx DRC, as well as a downloadable free version that covers 8 basic rules. All of these directly work with the Mentor Graphics PCB formats, and with its support of ODB++, it can be used with any of the major PCB layout design tools on the market. The electromagnetic interference rules highlight one of the great advantages of an analysis engine like HyperLynx DRC. Issues like high-speed nets crossing a split in their reference plane, or vertical reference plane changes through a via without a near stitching via or filter capacitor to supply the return current can be simulated. But the simulations are time-consuming and complex. HyperLynx DRC easily and quickly can find issues like these and other rules-based possible EMI sources. As you can see here, there's a wide range of signal integrity rules that can be checked as well. Validation of impedance and topology are just a few examples of geometric PCB checks that can affect signal integrity. There's also a group of power integrity rules available with HyperLynx DRC, as you can see from the list. The latest release added 2 new categories, an analog rules category and a safety rules category. The new safety category with its clearance and creepage checks is the focus of this webinar. For a detailed description, we went into the Mentor Graphics archive for a webinar recording that gives an excellent explanation of clearance and creepage issues and how HyperLynx DRC makes the analysis of these sometimes complex rules easier.
Welcome to a webinar from Mentor. My name is Rory Riggs, and today I will be discussing safety, creepage, and clearance with HyperLynx DRC. The flow depicted here is the typical design process for PCB. After the layout design and the design review are completed, the safety check is performed. If any design error was found, the layout design needs to be modified. Our customers say that the manual safety inspection can take days or even weeks to perform a safety check. Every time they modify the layout and the design, the manual inspection is required to be completed, which will cause the process delay you see above. Mentor has had many discussions with its customers on how they perform these safety checks and how tedious of a process it is. Some quotes here say it takes days to weeks and is very error-prone, painful process. And another customer said it's almost impossible to find all of the design errors manually as the PCB design is getting increasingly complicated. In order to protect users or maintenance persons, circuits that are accessible must be electrically isolated. For example, if you open the maintenance door of a copying machine, you are not expecting to see the motor moving. The motor and the power circuit need to be isolated. Another example is that when you're taking an electrocardiogram, you will never expect high voltage at the sensor. The minimum creepage and clearance distances are those requirements in order to have that necessary distance to disconnect the energy source and isolation. Dielectric material, for example, air, glass, or plastic, these are normally excellent insulators. However, they will break down at a certain voltage. Creepage discharge is also known as tracking. Creepage discharge is the flow of current along the surface of the insulation. So for safety, we need to consider both of these models. So here I want to go over what exactly is the creepage distance and the clearance distance and the differences between both. So the creepage distance is the shortest distance along the surface of an insulating material between the 2 conductive parts. And the clearance distance is the shortest distance in air between those 2 conductive parts. So you can see in all of the pictures here that blue will represent the clearance distance and red the creepage distance. Since the creepage distance is along the surface of the insulation, To gain creepage distance or to extend it, sometimes a cutout is placed between the path. So these red lines indicate that the creepage distances. The International Electrotechnical Commission, or IEC, is a non-profit, non-governmental international standards organization, and they're defining the electrical standards for safety, creepage, and clearance. They have standard numbers that range from 60,000 to 80,000, and these numbers indicate a title for a different area of electronics. Some examples are medical equipment, or audio video, or information technology, or power electronics. So as these standards are created, PCB designers will follow these standards in order to meet their requirements for safety. Each standard has a minimum creepage and clearance requirements. Though many of the standards share the same table, we need to refer to the correct table for our technology. To find the minimum creepage distance, we need to know the board material and in which condition that the board is being used. So first, we need to select the pollution degree. The pollution degree is the environment, like in a clean room. So that's pollution degree 1. Pollution degree 2 is the environment of an office. Pollution degree 3 is selected when the equipment is in an industrial area. For FR4 material, we can select material group 3. So for this example, we'll use pollution degree 2 and material group 3, and our working voltage will be 40 volts. So now we can use this chart to find the minimum creepage distance for our specific working voltage. If reinforced isolation is applied to that part, we should double the reading for our use case. This is the trickiest part of how to measure the creepage distance. It really depends on the materials of your board. We'll use the two pictures on the left as an example. We have a few different answers here depending on the material of object C. If we can disregard object C, then it's just the clearance distance between net A and B, the large distance. But if object C is a floating metal, which it most often is the case on a PCB, then we need to consider the two smaller distances, capital D and lowercase d in this example, when trying to figure out and calculate this creepage distance. Let's discuss with the top left picture, the side view of the board. We want to measure the creepage distance between net A and net B. If there is a conductive material or materials between them, then we need to take this into account. So if object C is a constant net, then A and B are therefore isolated, which means that we do not have to worry about creepage or high voltage safety. If object C is a floating metal, which is including a signal net that may have a high impedance, then we need to use and check with the 1/3 rule. With the 1/3 rule, first we need to measure the clearance distance, not creepage distance, the clearance between A and C, and then the clearance between B and C. These are going to be our lowercase d and our uppercase D distances. If these clearance distances are smaller than the 1/3 of the required clearance distance total, the object C is considered as a part of net A and or as a part of net B. So if both lowercase d and uppercase d are smaller than 1/3 of the clearance distance, then we consider that net A and B has zero creepage distance. Although the math is not very complicated, we are talking about addition of two values and doing a fraction of 1/3 clearance distance here. But the time it takes to understand the materials, look up their values in the chart, know if they can be considered as an extension of the net, this is all very time consuming and very tedious to do for every object on the PCB. And not only that, it is easy to make a mistake, to look at the wrong value in the chart, to measure the distance incorrectly, to not consider another floating object or signal net and have it affect other nets in the design. You have to be absolutely perfect with your analysis in order to validate your layout. The HyperLynx DRC creepage rules support various IEC standard tables. We have embedded in the automation of HyperLynx DRC the IEC charts for medical equipment, IT equipment, communication, and audio video, installation coordination, low voltage system and electrical power drive systems standard, and a power electronics standard. I want to discuss how we can perform automatic creepage checks with the HyperLynx DRC creepage rules. First, we will select the parameters, what environment or pollution degree our PCB is in, for example. Then, we will create net groups to select which nets we want to check in our layout. We'll call these object lists. And then we select a button for executing the rule and simply review the results. It's very easy to do. Now let's see a real example. The red highlighted net is a 200-volt high voltage net, and the blue net is a victim net on my design. The two nets are isolated with a cutout in between. The required minimum creepage distance is 4 millimeters in pollution degree 2 environment with reinforced isolation. Now let's show the view in HyperLynx DRC. This is what the checked result will look like. The red line indicates the shortest creepage path, which, as we expect, went along the cutout. The measured creepage distance was 3.862 millimeters, which is smaller than our requirement of 4 millimeters. If we manually inspected this board, this is the most probable result that we can get. And we have verified that here with HyperLynx DRC finding it automatically. However, HyperLynx DRC found another path as well. The 200-volt net is close enough to the signal nets so that we consider the signal nets are now part of that high voltage aggressor net. The shortage creepage path was found in a different place, and this distance was only 1.9 millimeters. So as we can see with this example, the creepage safety check is very complicated and an error-prone process in general. Not all examples are simple, just a short 4 millimeter creepage distance around a cutout. If you take into account how much time it would take to manually inspect each of these floating signal traces and consider them an extension of the 200-volt aggressor net and how it can creep to our victim net in this other area of our PCB, it would take hours to find this. HyperLynx DRC did this in a matter of minutes automatically for us. Now let's switch gears a little bit and talk about clearance. Clearance is much simpler than the creepage check, but with a real board can also become complicated. Typical FR4 has different withstand voltages values between vertical and horizontal directions. We may also need to consider different dilating factors. Unlike creepage distance, we consider the peak working voltage for clearance. The standard table is shown on the right. By the way, these tables are only applicable if the machinery will be used below 2,000 meters. If the altitude is over 2,000 meters, we need to multiply with a factor. HyperLynx DRC can measure the clearance distances as shown in these pictures. You can set the maximum withstand voltage for the outer layers, the inner layers, horizontally or vertically, or you can just specify the minimum clearance values. The rule can be duplicated in the system and set as a different set of parameter values depending on which nets you're trying to analyze. I want to reiterate the process of how to check for clearance in HyperLynx DRC. Similar to creepage check, you'll create an object list, which is just a selection of nets on your board. So you'll select high voltage nets and create a group. And then you'll set the minimum spacing values for the voltages for your rule. And then you'll just simply execute the rule and then review the results that come up in a matter of seconds. Now I would like to show you a demo of the same layer and multi-layer creepage checks using HyperLynx DRC. First, I want to start off using Expedition Layout, Mentor's layout design tool. We can run all the HyperLynx DRCs and HyperLynx DRC standalone on any layout, and we can also run them inside Expedition directly. So if we find an error in our layout, we can correct it immediately using our layout tool. For this example, I will use that 200 volt aggressor net with that cutout in between. Here we're seeing the top side of the board only from the pictures we talked about earlier in our webinar. You can see the victim net there on the top side. And then I'll switch to the bottom side of the board and show the connecting floating metal that we found in that second use case and the area of the board where we will find the second problem that only HyperLynx DRC found. Now we're switching over to HyperLynx DRC standalone mode to show you the rules here in the standalone tool. On the left side, I'll expand the rules and results and go to our safety category folder where we've grouped the out-of-the-box creepage and clearance checks here in this rule group folder. You'll see that we have 2 rules for same layer creepage checks and 2 for multi-layer creepage checks. The same layer creepage check is what we call the 2D creepage rule. So it's only checking objects and nets on the same layer on the PCB. There's one rule for just basic creepage distance checks and one rule for same layer creepage checks with the safety standards embedded in the rule. And these are those IEC standards we talked about earlier. The same thing goes for the multi-layer checks. There's a simple multi-layer creepage distance check, which will check the outer layers of the PCB. The multi-layer creepage for safety standards check does the same, but also has embedded those IEC safety standards if those are what you care about for your creepage checks. Expanding a little further on the same layer creepage checks, you can see that it's just the simple version of the rule where it checks the distance between object 1 and object 2. And since we're looking at creepage distance calculations here, it will mind the air gap and walk around the air gap. When we look at the safety standards rule, you can see that in the parameters window, the regulations for you can do manual input to put in your own manual creepage distance sets, as well as selecting one of the 6 embedded options for the rule. You also have the ability to select the pollution degree and the material group, as well as the layer for your checks, because this is the same layer check. It's as simple as clicking in the spreadsheet box and value and changing your pollution degree to 1, 2, or 3, or changing your material group, depending on which IEC chart you're using, what materials you have on your board, and the pollution degree of your environment. So it's very easy to set up the rule and target your specific use case. The next step would be just right-clicking on the rule and clicking Execute to run the rule. After running the rule and getting violations, we'll view the results in the Results tab of the spreadsheet and simply click on a violation. By selecting a violation for any HyperLynx DRC, it will change the view of the main window to show you where the violation occurs, what layer it occurs on, other nets that are a part of the violation. So in our case, we'll have the high voltage aggressor net, the 200 volt net that we're worried about creeping to other nets. And then we'll have the name of the victim net and its voltage, what layer it's on, the creepage distance, and then the required distance, which is all shown in the details window on the bottom right. So selecting the first violation, we want to zoom in here and view, you can see that red line that shows the creepage distance between the high voltage net and the victim net. We'll expand the details window as we see fit to look at our color scheme for what the violation is reporting. Lime green will be the victim net. You can see that this error occurs on the top side of the board. Now we'll move on to the multi-layer creepage check or outer layer creepage check for safety standards. Remember that the multi-layer check considers the board edge as well as through a via or through a contour. Zooming in on the violation we get after running the multi-layer check, we'll see a very tiny minimum or a very tiny recorded creepage distance, whereas we expect the creepage distance to be between the lime green victim net that I just highlighted and the high voltage 200 volt aggressor. We actually have an extension of the victim net here in dark green showing other considerations of what would be the victim net here because of their floating metal, because they're that object C in our example earlier. The clearance distance here would not just be between object 1, the main net, the main 200 volt net, and the lime green victim net. There's no just minimum creepage distance here around the cutout. The victim net is floating to these nearby metals and nearby signal traces. And so these are all extensions of the victim net. And so in reality, we don't have a creepage distance from here to here. We have a creepage distance from here to the extended victim net, which is very, very short. And I'll zoom in there to show you. So to find that manually by visual inspection, we would have to have analyzed the victim net and then calculated each of those signal traces with that 1/3 rule till we got to the point here where we're right next to the victim net, right next to the aggressor net, excuse me. And you can see here in the bottom right window that the actual creepage distance was very small, and our required distance was 4 millimeters. If we looked at this with our own visual inspection, it's very plain to see that we would think that we were within our required distance of 4 millimeters. It's very, very much apparent that our victim net is more than 4 millimeters away from our aggressor net. But in reality, by following the IEC standards, we have to consider these floating objects as part of our victim, and actual creepage distance was here to here. So we need to make some changes here with our high voltage power net, maybe move it, or put some insulating material here, put a cutout here if possible, and move some objects around. You can see that it takes these checks a little bit longer to run than some of the other rules in HyperLynx DRC, but the time savings is well worth it to have these checks run in a matter of minutes versus the hours or days it takes to find and calculate these creepage distances on their own. So here's another example of same layer with creepage safety standards in mind. Our required distance was 4 millimeters, and you can see the creepage distance was 3.7, so we're barely not meeting it, and it is walking around that cutout. I changed the view there to show you the cutout there in the board, that the creepage distance is walking around. And now I want to show in Expedition, we can run these same checks. So I'll select the multi-layer creepage check and then hit Analyze the Design. And in Expedition, we'll get a HyperLynx DRC folder, and by clicking on the rule, in the same way that we get violations reported in HyperLynx DRC, it'll just snap to the proper portion of the board. It'll highlight the active layer that the violation occurs on. And we can see using this multi-layer rule, we have a high voltage aggressor net on the top side of the board on layer 1 that is going through this contour or hole in the board, this cutout we made, and going down into the bottom side of the board and affecting our victim net on the bottom side of the board. So the multi-layer creepage rule will check beyond the same layer. It will check the outer layers of the board, and it will take into account through a hole or through a via or the outer edge of the board to find the minimum creepage distance. So now think about how complicated that could be when doing this manually with a visual inspection. You not only have to consider the floating object on the top side of the board, but then the victim nets in the distance through a hole in the board to the bottom side. So although the 1/3 rule is simple math, these checks can become increasingly complicated and time consuming when done manually. And since we're using Expedition, we actually can make these changes immediately. I can move that net immediately. I can choose to fix this problem right in my layout stage. And here, I just want to show HyperLynx DRC standalone how it also reports the same violation if you're using the standalone tool versus using it inside of Expedition. Let's look at one last example of a multi-layer creepage check inside of Expedition. So once again, I'm going to view my hazards and select the violation. And here I want to show how it will report a violation on the outer edge of the board. So here we have our aggressor net on the top side of the board, and you can see this net is here on the top side of the board. I changed the to shadow mode to make it very apparent where our victim is in green and where our aggressor is in khaki. So the 100-volt aggressor net is on the top side of the board, and it will go to the outer edge of the board and around to the bottom side of the board to affect our victim net here on the bottom side of the board. This creepage distance is automatically calculated with HyperLynx DRC here. To do this manually, we would have to go from the top side of the board and then get the distance around the outer edge of the board to the victim object on the bottom side. So you can see how useful these DRCs are in finding your safety issues and validating your layout. Here, we're validating the layout within Expedition, inside of the layout tool. So the time savings and the cost savings here for doing your analysis, for getting your PCB out the door to the prototyping stage, this allows you to get your circuits done faster and to have your time to market be a lot quicker for your design cycle. So now I just want to do a summary of what we talked about today. The creepage distance check can be done with just selecting and setting the following items. You just need to select which nets you want to check, your aggressor net, your high voltage nets, and victim nets on the board. You need to select the IEC standard type that you're going to use. You know the pollution degree of your environment and the material type. And then the HyperLynx DRC will do that whole 1/3 calculation clearance distance rule for you with the embedded standard of the rule. It can do this very quickly and very easily. You can do it in standalone mode on any layout that you design your circuit in. And there's the added benefit that if you're on a Mentor flow and you're using Mentor's Expedition tool, you can run these DRCs inside of the layout. Consider the floating metals in your design and how complicated this process can be. We're talking about validating a circuit that has layer by layer, net by net. You have to consider these safety checks, the clearance and creepage checks. This can take hours, days, or even weeks. So HyperLynx DRC can do this automatically for you. And you can find these in a matter of minutes. And so it makes it very easy to find and correct these safety issues that your PCB can have. We also have not only same layer 2D checks, but we have the 3D clearance checks. We have the multi-layer rules where we're checking the outer layers of the PCB, where we're checking the board edge of the PCB, and we're also checking through a hole or through a cutout in the design. So with these expansion rules, the multi-layer rules, we are covering more safety issues and more use cases for validating a PCB in a safety area today. And with that, I want to say thank you for watching this webinar on safety, creepage, and clearance using HyperLynx DRC.
Thank you for taking the time to watch that webinar. I think it was very informative and actually taught me some things about creepage as well. If you would like to know more about HyperLynx DRC, there are many sources of information available. Here is an overview of a few of the white papers available on the Metrographics website. And there's also recordings available describing the many rules-based checks that you can do. And there's literally dozens and dozens of recordings to cover all the different checks that I was showing you. Okay, that concludes our presentation